So this is the addendum to the Chapter 3 Chemistry of Life Organic Compounds presentation. I already did this part of the lecture and somehow it just didn't get recorded, so I guess I'll have to do it again. Where I left off and then some technical issue happened was I was talking about hydrophobic and hydrophilic, and that's a really key thing with fats, and it'll come back to haunt us when we look at membranes, which are made of fats, like these kind of fats. There. Okay, so what makes fats different from all of the other compounds we've studied is that they don't have groups like all these hydroxyls everywhere. Glucose has them on literally every single carbon. Here, and then there's one here. Amino acids, they have other hydrophilic properties such as the carboxylic acid and the amines. And well, long story short, fats do not. They are nothing but carbons and hydrogens, and these are non-polar. These are non-polar covalent bonds. Non-polar covalent bonds. They're also very high energy bonds. If we just lopped off this guy right here, you could put this molecule in some engines and it would run on it. It's just so high energy, generally longer. In fact, high octane fuel, oct, that means 8. That would mean that this number here would be an 8. And there would be 8 of these carbons, 1, 2, 3, 4, 5, 6, 7, 8, surrounded by hydrogens. They're all completely nonpolar, hydrophobic, and they have a really high energy. And that's one of the reasons, well, it's the reason, that fats have a higher caloric value than non-fats. Sorry, I'm having a cup of coffee if you heard that slurp. Okay, so lipids and fats. Firstly, what are they made of? Two things, at least two basic things that are pretty much always present. Glycerol, we've already studied that molecule. It's a 1, 2, 3 carbon compound. We could call it a trio sugar, I suppose, but people generally, I don't hear people refer to it that way often. It has on each carbon a hydroxyl. And remember, these hydroxyls govern the bonding properties of this molecule, and each of these hydroxyls can bond to a fatty acid. So we have one bond that is about to be formed here. It hasn't been formed yet. Let me erase that. And then we have another bond that could form here, and a third one that can form here. The result is what you see below. This is a triglyceride or a triacylglycerol. Generally, I'll just call it a triglyceride. It's a triglyceride. Triacylglycerol. Okay, fine. We can call it that too. I think this is a more specific name. Triglyceride, though, generally just refers to there being 1, 2, 3 of, I shouldn't have labeled it here, sorry. 1, 2, 3 fatty acids. These are the fatty acids. These long fellows right here, these are the fatty acids. They're called fatty acids because before this bond has been formed, that's called an ester bond or ester linkage. And yeah, sorry, you got to memorize that one. Ester bond. This is an ester bond. Before this ester bond is formed, you're going to have a fatty acid has in fact a carboxyl or carboxylic acid at the very end of it. And remember, this R just stands for a whole bunch of carbons. The remainder of the molecule, basically this whole thing right here. So this carboxylic acid is where we get the name fatty acids, and they can undergo dehydration synthesis just like carbohydrates, in that case a hydrogen and a hydrogen and oxygen are removed, and that forms one molecule of H2O. Dehydration synthesis, and 3 of those reactions can happen. 1, 2, 3, or 1, 2, 3. And if we want to kind of do this whole thing in reverse and perform a hydrolysis of fatty acids, then, well, let's see, if this is a carboxylic acid here, then, okay, oxygen double bonded to carbon, single bonded to another oxygen. This fellow is going to get bound to a hydrogen, like so. And then the carbon here is going to gain both a oxygen and a hydrogen. So oxygen and a hydrogen. And then everybody is made whole again. These ones are just over here. These are just examples of certain types of fatty acid. We'll come back to this right away, actually, and we're going to look at what does it mean to have these double bonds here and there versus no double bond. So a saturated fatty acid, remember these are a component of lipids. Saturated fatty acids, that we call them saturated because all of carbon's 4 bonds in the fatty acid chain, or the tail of the fatty acid, this part, they are, so all C's, carbons, fully bound to hydrogen. Remember, each carbon can make 1, 2, 3, 4 bonds, and in this chain, 2 of the bonds have to be to adjacent carbons. So we'll say this carbon right here, it's bound to 1 carbon, and then another carbon, and then its remaining 2 bonds, so that second carbon will be down here, I guess, then the second 2 bonds are here. So when we say saturated, what we mean is all of carbon's 4 bonds are being utilized as much as possible to bind to hydrogens. This makes for a fatty acid tail that is totally hydrophobic compared to this fatty acid over here. We have a double bond, and that's a region of more electrons. Double bond means a total of 4 electrons are shared there. So this gives the fatty acid a more hydrophilic nature. It is a little more attracted to water than otherwise would be. Often we can say that unsaturated fats, should I say often? I should say, I guess more generally we can say, generally more healthy. More healthy. So if you think about, and this is a dramatic simplification, but if you imagine these fats are going through your bloodstream and they're actually transported with a big group of proteins with them. But anyway, if you imagine these fats going through your blood, circulating around, you want fatty acids that are going to be more water soluble. So more hydrophilic means more water soluble. More water soluble, less likely to precipitate out on the edges of your arteries. So if this is an artery and you've got a fatty acid that is turning into a solid on the side of it, that means that is one of the things that contributes to plaque formation. And so once we've got a little bit of these saturated fatty acids there, then we can get more saturated fatty acids because they bind together with these hydrophobic interactions. And in the end, it's a bad deal. By the way, smoking causes these as well because nicotine damages the inner lining of blood vessels, and it sort of causes the sort of a sticking point for things like saturated fats, cholesterol, and then a whole bunch of other stuff like white blood cells and da-da-da-da-da. Side note, not part of this course though. Okay, so anyway, unsaturated fatty acids are more water soluble. That's good. Here we can see kind of a side note on that water solubility. When we have double bonds, unsaturated fats, they tend to be liquid at room temperature. So liquid at room temperature, one of the reasons is that these double bonds tend to put sort of a kink in the side chain in these fatty acid, not side chain, excuse me. These double bonds tend to put sort of a kink or a bend in the fatty acid chain here. And that means that these fatty acid tails cannot pack as densely together. So because they're a little less densely packed, that contributes to their liquid property at room temperature. I guess I should say melting. That's not really quite the same thing. Anyway, they're less dense because of these double bonds. Saturated fats, these are animal fats more often. They are typically solid at room temperature. You can see that no double bonds exist in the fatty acid chains, and they are therefore capable of being more densely packed. And ester bonds, that's what holds them all together. You got to remember that. Lipids, phospholipids. So this is where we're coming back to what I mentioned in the beginning of the lecture, and that is a phospholipid, or a phosphate group. A phosphate group, that's a functional group. Functional groups help determine the chemical properties of a compound and its bonding properties. Here, we're not interested so much in bonding properties as the chemical properties. So a phosphate group, we can see right there, is negatively charged. So that we can think of this whole molecule as a negatively charged, having a negatively charged head. There we go. It says it down there. Hydrophilic head, and it's hydrophilic because of that negative charge. Because of that, often we draw phospholipids in a simplified way, which is as follows, like that, and then okay. So these are the fatty acid tails, and then this is the hydrophilic head, which is composed of a phosphate group, this phosphate group. So what that means for us, because we're interested in living things, is if you throw a bunch of phospholipids into water, then they will sometimes assemble into this diagram over here. This is a phospholipid bilayer. What a big phrase. Phospholipid bilayer. So phospholipid means it's made of these things. Bilayer means there's two layers. So let me switch back here. Two layers meaning basically one layer on top, there's the phosphate heads, fatty acid tails, one layer on top, and then another layer on bottom that's sort of upside down. Okay, so a phospholipid bilayer. One layer there, second layer right there. And looking at a much better diagram right here, we can see that the phosphate heads that are hydrophilic orient towards where there is water. Water right there, see? And then on the bottom, these hydrophilic heads also orient themselves towards where there's water. Water on the bottom, because it's a watery solution. The hydrophobic fatty acid tails orient inwards and are sandwiched between the hydrophilic heads here in a protected hydrophobic core. Okay. Oh, and one more term that you need to know here, and that is amphipathic, right there. Oops. Amphipathic. What amphipathic means is that one part of the molecule is polar or hydrophilic, so it interacts with water, and the other part of the molecule is nonpolar or hydrophobic, so it is repelled by water. So we say the molecule is amphipathic. These amphipathic phospholipids. Say that 10 times fast, huh? Hydrophilic and hydrophobic. What was I saying here? This is, I guess, just the same diagram that I just showed you, but it's got a little bit, maybe it's a little easier to understand. So again, this hydrophilic head here, these structural details here, I'm not requiring that you know. I do want you to know, there we go, nice color here. You should be able to identify that this is glycerol. But again, the main thing that we're really interested in here is, well, three things, I guess. One, glycerol and fatty acids, 1, 2 in this case, make up phospholipids. And then there's also a phosphate group on the top, which makes the top hydrophilic, or rather negatively charged. Here, what we're seeing is a couple of other orientations of phospholipids that you can get when you throw it in water. This is a monolayer, and mono means one. So again, what we've got here is, let's use blue to show the hydrophilic region. This is the hydrophilic heads. And in this case, we just have a layer of them sitting on the top of the water, I guess is what they're showing here. And then the hydrophobic tails are trying to orient themselves away from the water as much as possible. or rather they are automatically repelled by the water. This is a mycel, and the interior is composed of the hydrophobic fatty acid tails, and the hydrophilic heads are oriented outwards. These are kind of starting to get some cool attention. Let's erase that. And that is because we're finding you can put drugs into them, and these things will sort of, if you do it right, they'll automatically fuse with cells and deliver the drug to specific cells. Kind of cool. You can put all these like kind of other parts on mycels that'll help them identify what cell they're supposed to go to. All right, and this is a vesicle, a bilayer vesicle, and this is actually the structure of a actual vesicle that we've talked about in chapter 4. Like, let's see, you could have transport vesicles, so maybe there's something getting transported in here. You could have a lysosome, in which case there'd be all these enzymes in here getting transported, hydrolytic enzymes. Hydrolytic enzymes, just a reminder, as we're talking about lysosomes, hydrolytic enzymes, that means they do hydrolysis, that same process we talked about with carbohydrates, water splitting, they break things apart. Anyway, same orientation, hydrophilic heads on the outside, on the sort of inner outside here, and then the hydrophobic fatty acid tails. Same story over here, hydrophobic fatty acid tails, hydrophobic fatty acid tails, and then the hydrophilic heads orient outwards. Alrighty then. Last slide on fats. This is a diagram of, you can see, cholesterol. Cholesterol is an essential component of animal cell membranes. So in all the cells of cell membranes, cholesterol is present, and it helps to stabilize them at both high and low temperatures, preventing them from like cracking if it's about to freeze, and then also preventing them from falling apart if it's really hot. Cholesterol is made from fatty acids. Fatty acids made from them. And you can kind of see it sort of looks like a fatty acid tail here, except that it's got a branch down at the end. And basically what happens is we have a fatty acid, and it just gets bent into all these funny contortions, and a few extra atoms are added, and then you get this four-ringed structure that we call cholesterol. Cholesterol, in turn, is a substrate for substrate. Substrate means like an ingredient. We'll come back to what that means in a later chapter. Or we could say the basis. Like, wood is what we use to build houses. So cholesterol is actually what we use to make hormones in the body. Hormones, cortisol. This is a steroid hormone, and that means that it is cholesterol based. You can see its structure is really, really similar to cholesterol. Testosterone and estrogen are other hormones that are based on cholesterol. Okay, and that is it for the fats here, and I hope you enjoyed fats.